Okay, so let's get started. I think the number of students has exponentially decreased. Is there any conflicting meeting right now, or you don't know where your friends are? Oh, grades for some other course. Oh, for this course. Okay, let's discuss more about this course in a second. Okay, so the plan for today is actually to continue where we left off in lecture 3B part. I think around slide 20. We will start there and continue to lecture 4 and so on. But before that, I wanted to spend a few minutes discussing overall logistics as well as the assignment. Okay, and assignment 2 is due, I believe, next week. So we'll kind of quickly go over it. So especially some of you who have started it, I know some of you started it because you've reached out to me with some confusion and so on. So if you have started it and you have some questions, now is a good time to kind of quickly discuss that. Okay, so where we are, just to kind of ground ourselves, we are at this lecture. And so the next assignment is due next week. The assignment content is about mostly just linear regression. So, and also gradient descent. So we'll discuss about assignment 2 in a second. I think 2 weeks from now, which is on 28th, I'm gonna send out information to each team for a particular slot. Team as in the team, the same assignment team, which is also going to be the project team. It's going to be meetings with individual teams. It's going to be online via Zoom, so you don't have to kind of wait here for 3 hours or something. So, but before that meeting, you have to submit something, right? So, which is basically an intermediate report and code if there's accompanying code, including a project plan. Project plan just means from Feb 28th onwards, what's your agenda for the next 8 weeks or so, right? So there's going to be the 4 of you. So who's going to do what is going to be explored, what is, maybe there's some ambitious things, maybe you'll drop it off depending on if you have bandwidth or not, but you want to kind of plan your sequence of steps, right? So planning is kind of important, so that you can hold yourself accountable in case you're lagging behind by a week or so. You can make that out by having a plan beforehand. Okay, so any questions regarding the scheduling and what the project entails? What the project requires is really, it's not a grandiose project that you're building something complicated. It's basically what you've learned in the course, which is not too much, right? So there's few topics that we've covered, but really spent a lot of time on them. And the project is about trying to build on those ideas, and some of the ideas that you've already seen in 572 or maybe in some other machine learning course that we've done elsewhere. I would suggest look at the project page. Let me open it to get a sense of like what the plan is. Although it's only talking about the final, I think the final deliverable here, the intermediate deliverable is listed here. It's basically for you to shortlist, be accountable. Okay, so why there is need for intermediate deliverable, although we only covered a partial set of topics, is because you can't wait till the end and then you suddenly realize there's a huge percentage of a grade depending on the project. But at the same time, the project is really, it's trying to mimic, of course, not fully, how you would have a short machine learning exercise in a company. Okay, so if you're, whether it's a big Fortune 500 or whether it's a small startup, things run in typically some development process, and you generally have a time frame, typically like a 6-month or even 3-month or whatever, even a 2-week sprint, for example, and you need to do something, right? And so at the end of that effort, you need to document it. And what you document is typically a report. It may not be a project report, but for us, it's a project report. But in professional settings, it's going to be some documentation, right? for posterity. So this page tells you what you would like to kind of focus on. The report, which kind of summarizes what you did, the accompanying code and the data that you used, and what you tried out. Okay, and the grading itself is based on these 4 factors: correctness, content, creativity, and clarity. I would not worry too much about creativity. It's super important to be correct. You cannot be using a linear model and keep saying non-linear models in your report, for example, right? It can't be doing regression and keep talking about classification, for example. Those are some very big mistakes, right? So try to be correct. Try to organize your content so that a third party who is not heavily involved with you for 8 weeks can get a good understanding of what was accomplished and what were some dead ends, and what they can take away with. Okay. Generally, it turns out the biggest takeaway for stakeholders is not so much the accuracy numbers that you're reporting, which is useful, certainly. Like, hopefully next time somebody else builds another model, maybe it has higher accuracy or higher, whatever the model metric may be. But there should be something beyond that. Okay, that's what we're looking for. Because if, let's say, you leave the firm and somebody else comes in, or some other team has to take over, they need to have the understanding of what you have done. Okay, and that cannot be summarized in like, hey, model 1 and accuracy number. Okay, so it's beyond that, right? Okay, so hopefully it should not be a big delta in the sense that writing and working through the project, because we do have an intermediate checkpoint. So if you're not well calibrated, this is a good checkpoint where we'll kind of calibrate your team so that you are kind of set up for success in this component. So I wouldn't say fret about it too much, but at the same time, start planning. Okay, it's good to go through that exercise. Okay, so what I'm going to do, as I said, is go over assignments. Okay, so does anybody have any questions about assignment 1, which was already submitted and graded, but I wanted to check. Okay, so as I suggested, the strategy is to actually do the assignment yourself. Now, I understand many of you are doing like 4+ courses, so which is hard to do. But at the same time, I think even though you're a group of 4, it will be good if you're ambitious and try to do the assignments yourself. Okay. Why do I say that? Is because the assignments are not complicated, but they kind of simultaneously are testing your Python Python proficiency, as well as some basic proficiency in working through machine learning modeling, right? So in professional settings, you may not be writing models from scratch. Okay, so you would not be. You'll probably be using a package, but to be able to use a package, to read its documentation, to understand, to get a feel for what functions can be called, how to instantiate objects from classes, which is, you can go through a documentation and figure it out, but that's a bigger delta than building your smaller functions first. Okay, so you take one step at a time, and so that is the motivation behind assignment 1, 2, and so on. Okay, that's the motivation. So I don't know how many of you use that strategy, but I know you can save time by splitting parts to between team members, but I would strongly encourage, try to do it yourself. Okay? And then debrief between the team members and submit an assignment, submit the assignment. So let me actually go back to assignments. So no questions about assignment 1, I presume, at the moment. If there are any, I would suggest you can always email me or the TA, because I suddenly asked. Of course, you may not have an question right now, but you can always email us. Okay, so that don't be afraid to contact teaching staff. You are in the learning mode. So okay, let's. So what I'm going to do, as I said, is briefly walk through assignment 2 because it's due next week, and then we'll get onto the content. Okay? So before I do a linear walkthrough, does anybody have a glaring question to ask about assignment 2 right now? Any major questions to ask right now? I know some students have already looked at the assignment, but for those who have not, I hope the logistics of assignment submission are clear. You need to submit a notebook and a PDF of the same thing. and there are various ways to create PDFs. I know some teams had some minor hiccups with creating this, but the objective is that the notebook should have the output cells, hopefully, saved when you save the notebook, and the PDF will also have the output plots or whatever is needed. Okay. So assignment 2, first question is all about gradient descent. We spent a lot of time on gradient descent, and the question is laid out in such a way that it's just giving you a rough scaffolding of how you want to code your gradient descent procedures. Okay, so most of it is actually, so all these points 1 to 6, actually 1 to, let's say, 3, are related to implementing the batch gradient descent. And so the most important ingredient in this gradient descent procedure, okay, is just how to compute gradient. Okay, and since we settled on using linear models and squared loss criteria, we know what the gradient is. Okay, we kind of saw in the lecture, so we can always write that gradient function. We can compute the gradient at any given input, okay, any given point. So the procedure itself has some interface, right? So this is basically what all inputs it can take and what outputs it will produce. Okay. So yeah.
So this the first part of the first question.
Yeah.
You're saying there is a gradient function.
Yes.
Are we assuming the loss function is the OLS loss? And
yes.
Model is linear model.
So at this step, it doesn't matter, right? That the batch gradient descent procedure, if you can give it a gradient function, it can do iterations, right? So whether you're actually solving a machine learning problem or some other gradient optimization problem doesn't matter at this point, right? But yeah, I think we talk about yeah. So this is the specialization. Okay. So here, the moment you swap the gradient function to some other gradient function, you can use, so that gradient function would correspond to potentially a different model and a different loss function, can potentially correspond. But all the information about, hey, we are working with linear models and we are working with square loss is captured in that only the gradient function. So the outer gradient descent procedure doesn't need to know that detail.
And the squared loss is the OLS squared loss or the mean squared loss?
So the difference is just normalization, right? If you
1/2 or 1/n. So
you can use either.
Either one.
Yeah. So the squared loss is just the sum of squares of the entries. You can always multiply that with 1/2 or 1 by the number of observations. So that's up to you. But I would suggest try to keep it consistent with the slides. But it's not a important thing for this. So as I said, the objective of this assignment is again to get you proficient in Python. If you're already proficient in Python, this should be easy, right? This should be like super quick. But I understand different people have different exposures to Python. So this is a good exercise, okay, and it will pay you dividends long term, over maybe a decade potentially. So first part is just setting up your like a wrapper function or a higher level function, which is this batch gradient descent procedure, which takes as an input a function. Okay, so functions are first class objects. You can pass functions also in Python. Okay, so that's, I guess, maybe throwing some of sometimes how to pass a function, but it's just like a variable. Okay, you can just pass a function. So what this is doing is a little bit of bookkeeping. It's returning all the iterates, so all the intermediate thetas, or basically all the intermediate thetas. It's also returning the final theta. That's hopefully is the best one according to minimizes the loss, and also some other things, which here it's written in a certain way, absolute and relative changes corresponding to the final iterate. So it's just it's basically a sense of like, when did you stop your procedure, right? So if you remember, the until convergence was the word we used in the lectures. What is until convergence? When the final iterate minus the final minus one iterate, if they're not too different. Okay, so that change, you can call it an absolute change, and you can say, hey, that didn't change too much. The absolute difference between those two vectors, for example, is small. Relative just means exactly the same thing. Final value minus the previous value divided by the previous value, for example. It's just things that you might have seen in other venues, right? So it's just a way to say, hey, when did you terminate, right? So you would have terminated at some point. So when you return something, you should tell, when did I return? This is a non-standard output. We're just asking for these outputs only so that you can potentially plot them and so on later. Okay. But this is the function signature that's suggested to you. You can always return other things, but these should be there. Okay. So part 2 is where the point is, this is the one which specializes to linear models and square laws. And so this needs a data set. So of course you need to find the gradient of the loss with respect to the parameter on a given data set. So data set is always fixed, right? So this function takes an input, the data set, and the point at which you want to find the gradient, point at which you want to find a gradient. Okay. Remember, if you remember the gradient coordinate, and we're going to go switch to slides in a few minutes. The gradient coordinate was like something like h theta of x minus y times xj. If you think of the jth coordinate, so there's an xj. So the current point xj value is also used to define the gradient of the loss with respect to theta j, that coordinate. Okay, so there is a need for the current point, and so that's why you need the current point. Like think of y is equal to x square, right? So y is equal to x square, the gradient of y with respect to x is 2x. So it depends on x. So you need x to say what the gradient is, right? So okay, it returns the gradient. So this function, should just take something as input and return the gradient, right? And then the third point is mostly using your procedure. Yeah, go ahead.
So with the second question, so you're talking about a point.
Yeah.
So X matrix has this two features, X1 and X2.
Two features, yes.
You're talking one of the points, let's say first row and X1. Like
no, one point just means one vector. Yeah.
The entire vector.
Yeah.
Okay.
So remember, gradient is the collection of the partial derivatives. So it's like a vectorized version. So if there are two features, and let's say you also had an intercept, then there would be three parameters, theta 0, theta 1, and theta 2. So your gradient would be three-dimensional. Okay. So first coordinate will be gradient of the loss with respect to theta naught. Sorry, partial derivative of the loss with respect to theta naught. Second coordinate will be partial derivative of loss with respect to theta 1. And third coordinate will be partial derivative of loss with respect to theta 2. Okay. So there's just three numbers. So point just means the two numbers. Okay. One. Oh, sorry. Yeah. I think I got confused here. So this point is the actual theta naught, theta 1, theta 2. Okay, sorry, I think I might have misspoke earlier. So this point is the theta naught, theta 1, theta 2. Is that not? If it's not clear, let me switch over to this. Let me just show some slide where it comes up. We'll see all this in a second, but let me get to gradient. I think I should have shown the other slide. I think linear regression. Okay, actually, let me. So let me backtrack. So just to clarify, in second question, you give a data set. So that's the data matrix and the labels. Okay. In this case, it's not the labels; it's the numeric y outputs. Okay, so that's the data set part. The point, I mean, the current value of theta vector. Okay, sorry, not the data point, but the current value of the theta vector. Remember, you want to find the gradient of the loss with respect to parameters, which are theta naught, theta 1, theta 2, three numbers, right? String them together into a vector. You're asking for what is the gradient of the loss with respect to theta at the current theta vector. Okay. So why is, and it should be clear that the gradient depends on the current theta vector because there is a h theta of x minus y. So there's a h theta there, so which is a function of theta. So you need theta to say what is the gradient. Okay. So that's the point. That's what it means by point. Okay. So for a two-dimensional problem, like two features, theta vector is going to be three-dimensional, like with an extra intercept. So those are those three numbers you need to pass in to get the gradient. Okay. Any other question here? Okay, so then I guess part 3 is just asking for hey, now you built this generalized nice batch gradient descent procedure or the function. Now let's actually pass a data set, right? So in fact, we are saying let's pass a data set with two dimensions. Sorry, actually it's a data set with one feature and one target. So the number of theta, there's only theta naught and theta 1. Okay, well, there's one theta corresponding to the feature and one intercept. And so your starting point, so this is the starting theta value. So we just pick some two numbers, one number for theta naught and one number for theta 1, some starting value, and then we want to iterate. Okay, so how many epochs and so on. There is some suggested choices here, but the objective of this part is just to try out the code that you wrote. Hopefully it works for this one-dimensional simple regression setting. Okay. And there's some plotting requests. I mean, so subparts just involve plotting. Hey, how did what do the gradients look like? So hopefully, as you iterate, as you do this gradient descent procedure for least squares loss, hopefully, as I said, the loss function looks like a ball. Okay, so in fact, yeah, it looks like a ball because there's theta naught and theta 1, two parameters to optimize for. So the loss function looks like a ball. And so hopefully, once you get to the bottom of the ball or near to it, the gradient values are going to be smaller. Okay? Gradient magnitudes are going to be smaller. Okay, so if you're far away from the ball, far away from the bottom of the ball, gradient magnitudes are going to be large. And when you're at the bottom of the ball, gradient magnitudes are going to be smaller. Okay, we saw this illustration, and basically the objective of this question is to recreate what we have in the slide deck. In our slides, we have a visualization, right? So that visualization actually corresponds to the two-dimensional search space, theta naught and theta 1. Okay. So just asking you to redo that. I mean, try to get to the same visualization, I guess. And parts 4, 5, and 6 are basically repeating with some slight changes in your definition of the some changes in the definition of the gradient descent procedure. Stochastic gradient descent just means there's no summation needed in the outer loop, and mini batch gradient descent means pick a small batch size, which is not the full data set, but also not one example. So that's the idea. And this part is interesting, which is part 6, which is now we change the loss function, okay, to a loss value which depends on the 4th power instead of the 2nd power. For this, what you need to do is actually compute the gradient, because I don't think we have an example in the slide deck of what the gradient is when your loss function is to the power 4. Okay, so you'll have to kind of figure out what the gradient is with respect to each coordinate, each theta value. So it's not difficult. I mean, this is just x to the power 4, y is equal to x to the power 4. How do you find the gradient, right? 4x to the power 3 times, 4x to the power 3, for example, is a gradient. But you need to do just use that idea here. So if you know calculus, if you've seen calculus prerequisite, if you kind of did that review, then this should not be difficult to handle. Okay. So here we're just changing a loss function. The model is still the same. It's a linear model. Okay, so the next question is about using a data set called the adult data set. I recently changed the link to, yeah, let's see if it works. Okay, so it needs UIC authentication. So this actually, let me mention it. Go back here. In case you don't find the data set on that link, which ideally you should let me know. Otherwise, otherwise you can actually get it from our folder. There's a data folder which has the CSV file as well. So in case you don't want, if in case the link didn't work and you didn't reach out to me, please, there's one more backup option to get the data set. Okay, so it's just in the folder which had the slides and the PDF version of the slides. It's the same. There's a data folder. Okay. So get the data set, and this is very similar to typical exploration you might have done in 572 or other courses. It's basically get a sense of, and this basically is an exercise in pandas. Okay, try pandas head, pandas describe, selecting columns, selecting rows, and so on. And looking at, hey, what are the unique values of the categorical variable, counting. So there are some nice functions in pandas. Okay, and that requires you to either go to pandas, pydata.org, and see the documentation. Okay, you can also look at a lot of people have replicated the same examples elsewhere, but get a feel for how to use pandas effectively. Okay. The second part is we want to now talk about the explicit regression problem, because we have built a procedure which can solve, in the part one, we have built a procedure which can solve for any linear regression setting. Okay, it doesn't have to be one-dimensional setting that was used in first part. So it turns out this data set is actually a classification data set. So we care about the class column, which is like whether a person earns over 50K a year or not. So there's a binary class. So the question is asking, can we solve it using linear regression? Okay, using linear regression. So we want to still use linear regression, not logistic regression that we're going to cover today. Okay, we still want to use linear regression, and we can partially use it. Okay, so there's no issue with even if its output is a class, we can still use linear regression, right? So for example, because it says whether a person earns over 50 or over $50,000 or less than $50,000, you can just map them to a couple of numbers, and so you have now a numeric target, and so you can use linear regression. And so that's what question 2 is asking. Hey, can you use linear regression? How to use linear regression is just a one sentence or 2-sentence answer, and then some other questions like balance. Is the data set balanced? And so on. So yeah, I guess third question is again just exploratory analysis. You should be able to see if there are some functionality in pandas itself to do the plotting between pairs of features. There's actually and it basically lets you explore the pandas documentation a little bit, and then perform linear regression using any one of your gradient descent procedures that you built. Okay. And then once you do that, then you can do some model diagnostics. What is the, there are some questions, it seems a little bit open-ended. So it's just asking, so what is the output? So just try to reinforce like what you already know. It's just trying to ensure that you are on the right track. So for example, there are some diagnostic questions like, are the residuals normally distributed? It's just something that you can potentially even plot and see. You can report visually. I mean, that's not the right way to do it, but at least you can report visually. Does look normally distributed, for example, right? And then also compare the result with what we saw using a formula. I think the last time on the we saw this normal equations, right? So that gave us this expression for linear models and squared laws. So we can try to compute theta according to that and see whether they actually matches with the theta that we got from using gradient descent procedure. And yeah, and it also actually this is where I think some cumulative effort helps. So it also suggests looking at compare the performance of this classifier against your previous classifier. So in assignment 1, you guys hopefully spent a lot of time building a classifier, dictionary classifier. So just call that, okay? And that's where you'll see that maybe there's a gap in the API or some extra functionality needs to be added or some things needs to be changed so that the dictionary can be called on this data set, perhaps. So that gives you a avenue to reuse your code. Now you're building on top of the preliminary things that you have constructed. Okay. The last part is actually partially related to today's content. But if you just look at this problem, it's just again an optimization problem of one variable theta. Instead of theta, we're suggesting optimize over alpha. But basically, just saying, hey, here's a function. I want to pick alpha such that this function is maximized. So tell me, how do you pick this alpha? So that's again a search problem, one-dimensional search problem. You have the last function. You just need to start with alpha naught, use a gradient descent procedure, and keep updating it so that at some good alpha, let's say alpha 1000, hopefully you have maximized your function. Okay, so that's just gradient descent again, gradient ascent, but you can you can answer these questions. Okay, so any preliminary impressions or any questions at this point? Yeah.
Can you start learn to use the decision tree to compare
No, it should be what you have written in assignment 1. You can use it. Yeah, what you did in assignment 1. Right? Yeah, what you wrote from scratch. Yes. Yeah. I mean, you can use scikit-learn's decision tree as well, but that need not be reported here. Okay, you see for all these questions, you already have a reference implementation. You can always call scikit-learn and see what the right fit is on your data, right? If you really want to know the, hey, is my theta completely off or is it correct? You can always call scikit-learn, model.fit, model.predict, and get a sense of whether it's a good fit or not. So definitely use these external tools, but for the purposes of the questions, yeah, most of this is like getting you to write Python while also working with the domain, which is machine learning, right? So yeah, good question. So anything else? Yeah.
So can we use a slightly different flavor of the gradient descent that we implemented in question 1?
Why do you have to implement a different flavor?
I mean, if it is a bit different from the previous pattern.
Oh, you mean question 3? It should ideally not be different. If it is, then you point it out and update your function. So ideally, yeah, it should not. So what you've written here for part 1 is not specific to linear models. Sorry, not specific to linear models. Part 1.1 is not specific to linear models. What is specific to linear models is the gradient function.
The reason I'm asking is because there are teams within teams, different people are doing different parts.
If you do, so if you want to manage, like split the task and manage, I know there has to be consensus, right? You cannot rewrite the gradient descent procedure again and again, and can't be a different gradient descent procedure on different questions. Yeah, I mean, so the thing is here we're not asking you to. So no part of this, let's say part 3 or part 2, sorry, these 2 questions is asking you to show the procedure again. Ideally, you would want to run. I mean, so try to write your own if you want, if you're doing separately, but at the end report one of the procedure. I mean, they all should be ideally, even if the variable names are different, the way you've written the for loops and so on inside is different, it's okay, right? There's a little bit of friction in combining it, but I would suggest not report your new procedures in these because it's not needed here, right?
Also, in question 2,
yeah,
since we are using linear model for a classification problem,
yeah,
so I could see that this requires a lot of feature scaling and renormalization. So, but that is not mentioned here. So, is this implicitly expected from us to do that?
So normalization and what else did you say? Scaling. No, normalization is scaling. What else did you say?
Feature scaling.
Uh,
Otherwise, our gradient descent procedure wouldn't converge.
So try out without doing these extra procedures, and if it doesn't converge, then you add this extra stuff and show that why that is necessary. So you just ask. So don't use things which are super complicated, okay? Because it doesn't. These questions don't need that. I understand for adult data set, there's some categorical variables, and so there needs to be some processing on them. That's a minimum requirement. But beyond that, whether you have to normalize each feature such that they're standardized in some sense, you should avoid it if possible. If it's really necessary, then certainly use it. Yeah. Because now the question arises: can I just use scikit-learn's functionality to do the renormalization or not? Try to avoid it. Try to keep your implementation without that. But if it really is needed, then
it wasn't converting after many. So
well, I mean, did you try changing a few other things that were the usual learning rates and so on?
Yes. So what is happening, because our this is a classification problem, so it wouldn't and there is one way.
No. Once you transform it to a regression problem, you should ignore classification.
There is a variable in our data set, which I mean the mean of that is some 48K.
Okay. Yeah. Yeah. So that's a numeric variable. Just divide by something. Right? So yeah, I agree. Yeah. So that's a good learning experience. You already gave a hint to everybody, but that one, I mean, you can just divide by x, right? So you don't have to use any further functionality. Right? Yeah, I agree. There's some normalization that you typically do if you use scikit-learn based workflow, but here try to not use external packages. Yeah, except for pandas, of course. pandas, NumPy, and matplotlib that we saw in assignment 1. Yeah. Okay, so let's actually get started. There seem to be some questions. Okay, so there seem to be some questions. Let me check what the questions are. Okay, so let's see what the questions are. Normalized distribution part. What is normalized distribution? Charu, do you have any comments?
Yes, Professor. So the question number 1 and
Actually, we can't hear
that,
you. So can you type it perhaps? Also, a quick reminder to folks, the screen is being shared, so don't write a direct message to me. Try to email me. Okay, so while Charu clarifies her question, let's see. So somebody asked, is output variable class column itself? Yeah, for the classification problem, the output variable is the class column, but you want to do regression. So how do you deal with that, class column to something else, right? So that's part of your question. C and R question. Plot the normalized distribution of occurrence of the values. Oh, so there's a question about in the regression in part 2. There's a question about show the distribution of values or something like that, right? I think it's just you can just, it's basically asking for histograms. Okay, so whether you write it, you normalize it explicitly, or you compute the counts explicitly, or use some pandas functionality, that's up to you. And if you use pandas functionality, there are going to be arguments which will say, hey, normalize or not. So I don't want to give more hints than that, but it's just histogram. Okay, so whichever way you can get, you can plot the bar plot. Radhika, I hope that's clear. Okay, so in the meantime, let me see. So now I think I can share. Yeah, so just focus on the last couple of questions. Okay, so for the balanced data part, should we check it for target variable? No, actually, yeah. I mean, balance just means balance with respect to the classes. So of course, it has to be with respect to the output class. For question 2, for each feature, plot the normalized distribution. Yeah, so this is just a histogram of in particular, categorical features. There's going to be different values that they take, and then you just need to count how many times they appear in proportion. Like, hey, 40% of the time, the categorical feature takes value X versus value Y, right? So that's the bar plot. That's being the question. Okay, so let me reset to screen share and everything. So see. So wait a second, there's one more question. Do we have to under or oversample the data set? No, it's just asking whether it's balanced or not. So there's no need to under or oversample. Okay, so wow, it took 45 minutes. So Radhika, you have a question, which is, are we using heat map to find correlation? No, it's just a correlation plot. I mean, you can use whatever you feel is appropriate to display relationships between features. So there is no, there is no right answer for that question. Okay, it's a little bit open-ended there. So it was about, again, part 2, there was something about features, relationship between features. So use whatever tools. I mean, there's no, as I said, it's a little bit open-ended only so that you need to gain confidence. Okay, in professional life, you'll not be given specific, directives. Of course, there's need for clarifying questions to clarify what is needed, but beyond that, you should be able to kind of come up with some satisfactory, analysis output, right? So, okay, so let me. So I'm not able to view chat when I'm sharing the screen for folks who are remote, and there are a lot of folks who are remote for some reason. Let's figure it out. Okay. Okay. Okay, so let's actually come back to our where we left last time. So we spent quite a bit of time on linear models, okay, and that was not because linear models are super complicated and we need to really understand all the nitty-gritties, but it was actually an exercise where very similar questions also come for any other model. Okay, it doesn't have to be just a linear model that we saw. It could be a deep learning model as well. So you need to have similar questions. Hey, how is the model specified? Does the gradient descent procedure work? Is the loss function appropriate? Will it overfit? Is how do I deal with features? How are the features getting through? And eventually we're getting a prediction and all that. So typical questions that you would see, right? Of course, there are some precise questions that you might have seen in perhaps in other courses, like doing hypothesis testing, like where you have a null hypothesis where all the coefficients are 0 and you try to reject the null and those types of things. If you've seen it, typical packages like scikit-learn or R packages or even stats models, there are packages which will report those things for you. Okay, so but that is beyond the scope of the lecture because we really want to focus on some of the properties, and so we are kind of not looking at some other properties. Okay, some aspects. So let's actually move to what we're going to do now is we start with KNNs and decision trees, and then we spent quite a bit of time on linear models. And that was not just about linear models, but it is also about gradient descent. Okay, the same template works for any differentiable model. Okay, gradient descent procedure, computational procedure. It's a big toolkit, kind of applies even for deep learning models. Okay, state-of-the-art deep learning models. Now what we're going to do is come back to linear models and say, hey, can we deal with some can we deal with data sets which don't exactly conform with linear model setting? Okay, one thing that you can always do with linear models is if you have the raw features, you can always transform them. I think somebody mentioned, Zoe mentioned a couple of times, and some folks mentioned last time as well. So you can always do feature engineering. Like the original number is, let's say if your original feature is numeric feature, you can take a log of it. You can make an exponent out of it. If you have two numeric features, you can multiply them. You can create polynomials. So you can do a lot of transformations from the raw feature vector into a transformed feature vector, where the transformed feature vector could have a dimensionality which is 20, where the original dimensionality might be 4. Okay? But once you have the transformed feature vector, which is 20 dimensional, from there on it's linear. Okay, but if you think of from the original feature vector, it's not linear. Okay, so there was some nonlinear transformation potentially happened, and then you eventually are doing some linear transformation. Okay, so other regression, which is what we saw last time. Okay, so that is already a big strength. Okay, so linear models are not really limiting in that way because you can always do what you have to do potentially manually, but you can always work with nonlinear. You can always build nonlinear models of the raw data. You can create derived feature vectors. Okay. So what we're going to do next is expand on the model side, by which I mean instead of linear models for regression, we are going to try to see, hey, linear models, can we extend it to, for example, classification, and today we'll see logistic regression as an example of that. But that's just one instance of a larger, I guess, a template of building such models, which is called generalized linear models. Okay, so it's rooted in statistical way of thinking. We're going to switch gears from computation, which is what I guess we spent a ton of time previously with linear algebra as well as gradient descent to a statistical perspective. And this is not, it's not that this perspective is, is the only way to build machine learning models, but for the class of models which need linearity, okay, which need linearity not just for maybe that's suitable for the data set, but also for interpretability and all that. This statistical perspective of generalized linear models really helps. Okay, it kind of extends beyond linear models for linear regression. Okay, so so let's start with this is the slide number 20, I guess, of lecture 03B. Okay, where we're transitioning off to basically logistic regression. So the question, the starting point is, can we use linear regression for can we use linear regression for predicting in a limited range? Okay, so we can use linear regression to predict a real valued number, and by definition of the linear function, the output can be anywhere. Okay, it can be minus infinity to infinity. Okay, so the question here is, can we use linear regression to predict when we know that the numbers have to be between 0 to 1? Okay. And that restriction is not exactly possible. I mean, at least naively not possible if you want to just predict between 0 to 1, because numbers by default will be potentially out of this bound. But you can always apply a post processing. You can say, hey, numbers greater than 1, I'll switch it to 1. Numbers lower than 0, I'll bump them up to 0. You can always do that post processing, but naively they don't help. Okay, and so what we can do is do this exactly this squishing procedure or transformation in the output. Okay, where we map just means again a function, right? So we map minus infinity and infinity range, okay, that range to the range 0, 1. So think of a function which takes an input, a number between minus infinity and infinity, and produces a number between 0 to 1. Okay, so we're gonna add that extra function into the mix. Okay, so of course with that extra function, the original model specification is no more linear. Okay, with that extra function, but there's going to be a linear part of it, and that's why I guess the logistic regression, that's what leads to logistic regression. Okay. So the original function for linear case was this, right? H theta of x is just linear transformation of x. Okay, it produces a number between minus infinity to infinity. Now, what we asked in the previous slide is, can we map using some what is called link function? Okay. And we're going to kind of represent it G. Okay. And here's an example link function. H theta of x is equal to the original x theta transpose x, but now with extra processing step. Okay. First compute theta transpose x, whatever number it produces, it's going to be a real number between minus infinity and infinity. Apply G, which now maps that thing from potentially from minus infinity to infinity to a value between 0 to 1. Okay. So here's an example G function. Okay. Looks like an S here. So basically saying anything negative, G of that number is 0. Anything positive and greater than 1, the G of that number is 1. And anything between 0 to 1, the G of that number is number itself. Okay, that's what this illustration is. This is a valid function. Okay, this is just squishing the output so that it's between 0 to 1, right? But there are some issues, especially since we kind of pivoted to gradient descent as our way of approaching and computing parameters of these models. The issue is basically that this function is continuous, which is good, which is a desirable property, but it's not smooth. Okay, so the gradient at these at value 0 and 1 at the input 0 and 1, it's not well defined. Okay, it needs a little bit more definition. Okay, so it's not that it's completely a completely impossible thing to overcome, but it's just something that is not amenable. It makes the thing a little bit more complicated. This non-smooth property. Non-smooth just means it needs to have a derivative at every given point of the input. Okay, so here the derivative is not well defined because there are too many derivatives. Okay, at this point and this point. Okay. It's also not. I mean, maybe minor point is that it's G of 0 is not 0.5, which because we are trying to map minus infinity to 0 to 1, you would imagine 0 will map to something like 0.5, but that's not the case here. But you can kind of fix it by shifting it to the left by 0.5. Okay. So here's a popular link function we are studying. It's called a logistic function or the sigmoid function. Okay, so it's mapping from the given domain to the range 0, 1. this square bracket means it's a closed set. Okay, it's just it includes 0 and 1. And g of z, the function link function is 1 by 1 plus e to the power minus z. Okay. So it's a seems like it's it's a function which has a numerator, denominator has an exponential function as well, but it's not too complicated. Since it's a function of one variable, one input, we can plot it, right? So if you plot it from minus 6 to 6, and if you just compute g of z for z is equal to minus 6, it's almost close to 0. G of minus 4 is something slightly less negative, slightly positive, and g of 0 is 0.5, which is nice, and g of 6 is almost close to 1. So this function is also actually similar to the previous function. It's actually what it's doing is g of, let's say, 20, it's almost going to be 1. G of minus 20 is also going to be 1. So it flattens out. Okay, very similar to the previous function. The only difference is that it has some curvature here. Okay, so it has some smooth property in the sense that there is no sudden change from one direction to another direction. So this is the sigmoid function. Okay, and yeah, I think we just mentioned that it's smooth, which just means it's differentiable at every point. And g of theta is g of 0 is 0.5. Okay, so now we can use this function to define our model specification. Okay, so we're going to kind of move away from regression to classification in the next few slides. But one quick point here is that, and we're going to use it a few slides from now. So I just want to mention that here, g prime of z, which is just the derivative of g with respect to z. Z only has, g has only one input, z, right? So if you take the derivative of g with respect to z, and then it turns out there'll be some messy expression if you write it in terms of all these exponents and all that. But if you write it in terms of g itself, it's actually equal to g of z times 1 minus g of z. Okay, this is something that we don't want to derive it right now in the class, but it's a good exercise for folks who want to exercise their calculus, calculus expertise. And especially it's a good exercise to do, not just because of this, but also because this is a function that you'll see many times. Okay, many deep learning model training you will have a sigmoid function somewhere or the other. Okay, so let's actually now talk about classification as a setting compared to regression and regression for classification ideas that we discussed before. So let's say we want to do STAM classification, and this is something, it's an illustrative example that you might have seen in other courses as well. So here's a particular way of feature encoding. So x1 to xn, just kind of, we are focusing on n particular words and seeing how many times did they occur in the email. Okay? So it's just although the email has a lot of words, we're just looking at a few words and saying, hey, how many times did the word occur in, how many times did the specific word occur. Okay, so x1 is number of times the word winner occurred, and so on. Okay, now given that this is the vector, so get any given email, you can get this n-dimensional feature vector. Okay, so which is all numeric, so there's no words here. Given that, we are gonna explicitly model h theta of x is equal to g of theta transpose of x. So now h theta specification now no more linear because there's a g in front of it. It's g in front of the linear transformation here. So it's not linear anymore. So we're going to define h theta of x like this. And then h theta of x itself, because it's a number between 0 to 1, we'll say, hey, that we're going to kind of equate it to the probability of y is equal to 1 given information, given basically x, the feature vector, and the parameter. So given the feature vector x and parameter, I'm going to say the probability of y is equal to 1 is going to be defined to be h theta of x, because and h theta of x is going to be this. Okay, and this is the odds, or this is the probability of this input email, which is captured by this feature vector x, to be spam. Okay. Is that clear? This is the specification of our model that we want to use. This is not something that this is not something we derived as such. It is just, we are saying that we're going to define h theta to be this, and we're going to say h theta is exactly the probability of one of the classes. And probability of the other class, let's say it's a binary classification for now, we're going to change it to multi-class maybe end of this lecture or beginning of next lecture. Probability of y is equal to 0 is just 1 minus that. Okay, So and this is we are imposing because the probabilities have to add up to 1, then the probability y is equal to 0 is just 1 minus h theta of x. Okay. Now for a generic point, so for a generic pair x comma y, for a generic pair and generic email and its label spam or not spam, probability of y given x can be written in again, this is a shorthand. Okay, so let me spend a couple of seconds here. So probability of y given x is written as h theta of x to the power y, okay, times 1 minus h theta of x to the power 1 minus y. Okay. This is just a shorthand. We could have written the probability of y given x and theta to be slightly differently, right? We could have just written, hey, if y is equal to 1, then it's h theta of x. If y is equal to 0, then it's 1 minus h theta of x. That's what the previous two sentences say, right? Instead of that, we wrote it in a compactified notation, which is, hey, if y is equal to 0, then only this term survives, because anything to the power 0, we're going to assume that it is 1. Okay, and so only this term survives. So if y is equal to 0, then it's 1 minus h theta of x, and if y is equal to 1, then this term doesn't survive because it's it's to the power 0. So this term is gone, and we only get h theta of x. So it's like, it's a nice expression. It's a trick. Okay, it's not something that you would naturally pick, but we picked this, and it has nice consequences later on, okay, for fitting the model, estimating the model, and so on. Okay, so that leads us to the logistic regression specification. Okay, so we motivated span classification, and we said, hey, let's think of the positive class, probability of the positive class given feature vector and theta to be something. So that leads us to definition of logistic regression, where we start with the data set and we say, hey, data set definition, we have seen it several times. So the likelihood of the data under any given theta. Okay, so we have seen this expression before a couple of times. So it's the likelihood of the data given theta is just likelihood of the data is just a probability of the data. Okay, so given at the given parameter theta, it's just a probability of the data. Okay, so remember for the linear regression case, when we're doing the likelihood interpretation, we said, hey, let's not worry about the randomness in x's. We don't care about randomness in x's. X's, let's think of them as fixed. The random variables are y's. Okay? When we're talking about linear regression, we talked about y's being random variables because epsilons are random variables, if you recall that lecture. So likelihood of the data just means the probability of these random variables y's. Okay? So probabilities of random variables y's given information related to them, which is the parameter theta and x's. Okay, and there's a product. So this big pi, Greek symbol pi, is just a short form for, again, a product of all the little m data pairs. Okay, little m examples in my training data. Okay, so this is I is equal to 1 to m of the product of all these probabilities. Okay, so probability that y1 is some value, y2 is some value, and so on. Okay? Superscript 1 is some value, superscript 2 is some value, and so on. Okay? Now this expression in this probability in the previous slide, according to the previous slide, is this expression. Okay, so it's h theta of x to the power y and 1 minus h theta to the power 1 minus y. Okay, now we are only talking about two class of binary logistic regression here. Okay, so far we'll eventually make it multi-class much later. So for now, just think of binary logistic regression. We are saying that this probability, and you saw in the previous slide, this probability, let's say for y is equal to 1, is exactly h theta of x. Okay, and h theta of x, we said it's g of theta transpose x. And what is that g? It was 1 by 1 plus e to the power minus z. So there is this, we are building a parts. We have the linear part, and then we applied this transformation g of z, which was the sigmoid function, and that is by definition h theta of x, and that we are saying is equal to p of y is equal to 1. Okay, and so since we didn't want to explicitly write, hey, y is equal to y subscript I, is it 0 or 1? We didn't want to explicitly write, and so that's why you use this exponentiated notation. Okay. Okay, so if you write the log likelihood, and that's where one, I guess, benefit of writing this way is that when you write the log likelihood, which is log of the likelihood, okay, log of product of terms is the sum of those log of those terms. Okay, so log of a times b in brackets is equal to log of a plus log of b, right? So that's what's going on here. So this product here became a summation of I is equal to 1 to whatever the number of data points are, let's say 100. And we know that log of a to the power b is b log a. So whatever is to the power, you just bring it to the as a coefficient. Okay. So there's the power yi, you just bring it as a coefficient. So yi log of h theta plus 1 minus yi of log of 1 minus this. Okay. Now when can you apply log, right? So log only makes sense for log has a domain. Okay. So it's a log is a function, it has a domain, and it can only be between 0 to infinity. So you can't pass, you can't find log of -1. Okay. It's not defined. So, but it satisfies. So likelihood, probability is always positive. Okay, so there it is between 0 to 1. So you can apply log. Okay. And so all these, and also we just remember h theta. Remember, it's always between 0 to 1. So it's in the right range. So you can apply log. Okay. So this is what likelihood term corresponds to. And once you have this, you can again use the batch gradient descent, stochastic gradient descent, mini batch gradient descent, whatever procedure you've written to optimize this likelihood function. Okay, it's a function of data, right? It's a function of data. The only missing thing is theta, which is still the parameter which does theta transpose x, right? It's just that the objective function is this more complex looking thing than just a sum of squares. Okay. Sum of squares was what you had before for linear regression. Here you have a slightly different objective, and you need to optimize over theta. And instead of minimizing, we're going to maximize because we have this log likelihood. Okay, we want to maximize, find that theta that maximizes the likelihood of this data that we already observed. Okay, so that was the definition for that was the the definition for maximum likelihood estimation. So you just need to maximize over either the original likelihood or the log likelihood. Okay, and the point here, and it's related to assignment question number 3, assignment 2 question number 3, is that whether you maximize the likelihood or whether you maximize the log likelihood, your answers will be the same. Answers for the solution theta will be the same. Of course, the objective values are in fact going to be different. One number will be log of the other number, for example, here. So so that's what you do. So at this point, you can say, hey, I already have the procedure, gradient descent procedure. What I just need is let's say the gradient of the loss, a gradient of the likelihood, or gradient of the log likelihood with respect to theta. Okay. If you can supply a gradient function, then you are done. You can find theta hat. Okay. So you can apply the same idea here, except everything is hidden in the gradient function, and you'll see that in the next few slides. Very interestingly, the gradient function also is the same gradient function that we saw for linear regression. Okay. So that's, I guess, a teaser, but let's actually do that. Okay. So this question, I guess, is now obsolete. Do we have ways to find maxima of a function? Okay. And the answer should be what? Was it? Yes. So the answer is yes. We have a procedure, and the answer and the procedure, if you want, is gradient descent. So gradient descent allowed us to find local minima, but you can do you can do a couple of tricks. One is maximizing a function is the same as minimizing the negative of the function. So you can just just say I want to minimize the negative of the function now, and just use gradient descent, or do gradient ascent on the original function. Okay, so gradient ascent just means going up the gradient. And so if you remember gradient descent, there was going in the direction of negative gradient. Instead of that, you go in the direction of the gradient itself. Okay, so those are two approaches. So question 3 in assignment 2 is about gradient ascent, or basically, you want to maximize the function. Okay, so whichever you do it, you can do it. Here we have written, hey, we can minimize the negative log likelihood. Okay, that's good. So the MLE, so let's actually pick the generic point, x comma y. So log likelihood is just y log of h plus 1 minus y log of 1 minus h. Okay. What we're going to do here is try to actually compute the gradient, and we'll see that gradient is the same as what we would have gotten for linear regression. Okay. Is the same as what we have gotten for linear regression, although in linear regression case we had the square loss and the h theta was different. Here the h theta is different because there's an extra g in front, and also the loss function is different. It's a negative log likelihood, let's say. Okay. Here let's focus on log likelihood. Negative log likelihood is just the same with a minus term in the front. So although the objective function is different, the hedge thetas are different. Turns out the gradient is going to evaluate the same. So, okay, let's find the gradient with respect to one. Let's try to find the partial derivative of the loss. Not loss. Let's try to find the partial derivative of the log likelihood with respect to one coordinate theta j. Okay. Why one coordinate? So think of gradient. Gradient is just the collection of these partial derivatives. So let's focus on one coordinate. Okay. And so if you look at this term, you have log of something. Okay. So its derivative is 1 by the term inside h theta times the gradient of the term inside with respect to theta. Okay. So this is just chain rule. For those of you, try to go back to your calculus refresher. The first term is just y times log of something is just y times 1 by the argument of the log function times the gradient of the argument of the log function with respect to theta j. Okay. Similarly, for the second term, it's the same thing. The coefficient times 1 by 1 minus h theta. Okay, so that's this. There's a minus sign because gradient of this produces a minus sign in the front. Okay, this minus sign here. Okay. So you can eyeball. So I don't want to spend too much time on this. Just algebra here. So this is the partial derivative of loss with respect to one coordinate is this. Okay. And here's where the fact that we saw 2 slides ago comes in. 2 slides ago, we said the gradient of g theta, the gradient of g, remember, is the sigmoid function. Remember, gradient of g with respect to z is g of z times 1 minus g of z. Right? 2 slides ago, let me, if I can go back. Here, gradient of g of z is just g of z itself times 1 minus g of z. So we're going to use that here. So g of z is here theta transpose x. So g of z times 1 minus g of z. And then what is the gradient of this thing? This thing we know the gradient is just xj. Okay, so the last term is something that we saw even when we were dealing with linear regression. The last terms, the partial derivative of theta transpose x with respect to theta j is just xj. Okay, so that's great. So now a lot of things simplify. So you can see that there is a g theta transpose x here, g theta transpose x getting multiplied. Similarly, there's a 1 minus g theta transpose x in the denominator and also in the numerator. So if you multiply all of them, so you get a term like this: y times something minus 1 minus y times something else. And if you open up the brackets and multiply and all that, you get a coordinate of the partial derivative to be y minus g of theta transpose x, the whole times xj. Okay, so what I'm trying to say is the log likelihood derivative, the derivative of the log likelihood, okay, is just in a given coordinate theta j is just a difference between what your prediction is versus what the truth is times xj. Okay. And remember this truth here, although we are using y notation, this truth is either 0 or 1. Okay, so we are in binary classification setting. Yeah, so to summarize, all these steps, if you don't want to pass through them, to summarize, the gradient of the log likelihood with respect to theta j is just y minus h theta of x times xj. Okay? And this expression should be what is similar to what we did in linear regression case. So let's look at the negative log likelihood. Negative is just 1 minus that. So negative is just minus times that. So minus of the term, and so we absorb the minus and just switch the locations of the h theta and y. And so if you want to minimize the negative log likelihood, then we just apply exactly our Bayes gradient descent procedure. Okay, it's just theta j is new theta j is old theta j minus learning rate times the negative the gradient of so basically this thing, which is just this expression here. Okay, so h theta of x minus y times xj. So this is our gradient descent procedure to estimate the parameters of this logistic regression model. The logistic regression model here for binary classes is just an extra g in front. Parameters did not change. It's exactly the same parameters as the linear regression case. Okay, so yeah, so that was for generic example, all this derivation just to get the expression for the algorithm. And now if you have the full data set, the batch gradient descent or whatever, the vanilla gradient descent, would just have a summation over all the m terms. Okay, and this should be clear that each term will have same type of an expression. So you average over all the elements of your data set, all the examples in your data set. Okay. So that's the summation here. Now let's actually recall linear regression's setting just to kind of compare and contrast a little bit. For single training example, a generic training example x comma y. For linear regression, it was very similar expression. So theta j new is theta j old minus some learning rate times an expression like this, h theta minus y times xj. Okay, and for all examples, it will be an extra summation of m here. Okay, and so given these two expressions, I think in the two different slides, the update rules look exactly the same. So theta j is theta j minus alpha times some summation of this expression. So what is the, so I guess here it's a good check. I already mentioned this, but it's a good check. So are they, what is the difference between these two? Given the update rules look exactly the same, what is that we're hiding underneath the carpet here? Yes, yes. So as she mentioned, the h theta definition is different. Okay, h theta is slightly different for the logistic regression case, and the loss function is also different for the logistic regression case. Okay, so but given those two differences, it turned out that they have the same expression, and that's not actually a coincidence. Although that's what it's asking here. It's not a coincidence. It turns out for the generalized linear models class, you will have a very similar gradient update rule. Okay, so optimizing our generalized linear models is actually you have a same template, and you can kind of specialize it to any link function and so on. So let's actually quick question. So if you have an update rule like this, theta j is updated by theta j minus alpha times the gradient of the loss with the gradient of some cost function with respect to theta j is a descent algorithm. The ascent algorithm would be what? Yeah, there's going to be a plus here. Okay, so in the direction of the gradient would be an addition. So in the direction of the gradient just means think of theta as vectors, right? So you're just thinking a vector addition. Okay. Yeah. And I think we discussed this earlier. Is the result the same if you do gradient descent on the log likelihood? So is the result the same if you do gradient ascent on the log likelihood of the logistic regression case? Yes. So whether you do a gradient ascent on log likelihood, or whether you do gradient descent on the negative log likelihood, you get the same answer. Okay, so there is no surprises there. So just to recap, and we'll take a short break right after, is we have seen linear regression. We kind of related it to, in particular, we saw linear regression and did a probabilistic interpretation of the model, right? So where we were justifying the squared loss. So we said, hey, if we assume that the conditional probability of y given x and the parameter theta is normal distribution for some mean and some variance, okay, where the mean is related, of course, to x and theta, then our problem, the squared loss problem that we kind of defined earlier, kind of is related to the maximal likelihood estimation of the data, which is y's, and try to find the theta that maximizes the likelihood of this data, right? And if you recall, mu is represented as a function of x and theta by what? Mu is actually equal to x transpose theta. Okay? That's how we interpreted when we gave this probabilistic kind of motivation for linear regression. Okay? Logistic regression is the following interpretation. Okay? So the following interpretation is the following. So y given x and theta is Bernoulli distributed. So y is Bernoulli distributed given x and theta. Okay. Bernoulli just means a random variable which takes two values. Okay, because we had a two-class classification. A Bernoulli, like for example, a coin toss is a Bernoulli event. So it's a Bernoulli. So we are saying the logistic regression for two classes is actually, we are assuming that y given x comma theta is Bernoulli, okay, with some parameter phi. Okay, so again some Greek symbol here, phi. And phi will be related to x and theta, whatever is given. This perpendicular sign just means the things on the right hand side of perpendicular sign are not random variables, or the values are given, so they don't have to model them explicitly. Okay? So Bernoulli, if you remember, probability of y is equal to 1 given the parameter phi. Probability of y is equal to 1 is exactly equal to phi. Okay, so if Bernoulli random variable has, if a coin has a bias of 0.4, then probability of, let's say, heads is corresponding to the random variable value 1, then the probability of random variable y taking value 1 is just the bias, which is 0.4, and probability of the random variable taking 0, which is the tails happening, is 1 minus that. Okay. So logistic regression actually corresponds to this interpretation, where we are saying that y given x comma theta is Bernoulli. Okay. So very similar to linear regression, where y given x comma theta is linear. Is normally distributed. Okay. Let me actually. So what we have not specified here is what is the relationship between phi and x and theta. Yeah. So what is the relationship between phi and x and theta? And that's exactly what we already defined in the previous few slides. I think I'll mention it in the next slide. But before that, I want to quickly mention this notation. Okay, so y given x colon semicolon theta, right? So y given x just means y is a random variable, and you're asking for what is the distribution typically of this random variable given typically another random variable. So when again random variable is given, you don't have to talk about its probability, because that's the probability. The random variable has already realized you only been given its value. The semicolon is to separate out, at least in the frequentist interpretation, things which are not random variables. Okay, so theta is not a random variable, at least in this modeling approach. Okay, so it's just saying y given a random variable and things which are not random variable, which are parameters here. Okay, there is a completely different approach of looking at these things, in particular Bayesian approach, where theta could also be a random variable, and so then you will not have a semicolon here. You just have a comma. You have two random variables. But for now, for us, it's just this is the approach we're going to take to get an understanding of linear models, logistic regression, as well as the exponential family and generalized linear models. Let's take a break now and resume at 4:32. And if you have any questions, you can come forward. Okay, let's actually resume. And so what we did was actually a roundabout way of getting to the definition for logistic regression in that binary case. Okay, and the roundabout way kind of landed us at this point where we are saying that y given x and theta is Bernoulli distributed with a parameter phi, and we have to say what phi is. In the linear case, in the linear regression case, there was a parameter mu, and we said mu is actually equal to theta transpose x. Okay, and we just need to say what is the relationship between phi and x comma theta in this summary of logistic regression for binary case. Okay, and we've already seen the answer, which is that this phi is the bias of the Bernoulli random variable. So this phi is actually equal to g of theta transpose x. So this phi is nothing but g of theta transpose x. So let me, yeah, I mean, I guess we'll see that in one more slide. So, but the question you can ask at this point is, hey, there are different specifications, different distributions here. Actually, one is normal, one is Bernoulli, and although there are different distributions, how are we getting the same type of update rule? Okay, different distributions, different loss functions, basically, and different model specifications, and we're getting the same type of update rule. And so that should be the question that we will try to disambiguate in the next hour or so. But the short answer at this point is that they are special cases of generalized linear models. Okay, so there is some linear component that exactly is the theta transpose x component, and there is some choice that you are making, okay, which is through this something called link function, this g function. Okay, if the g function is the identity function, what is an identity function? X is equal to x, y is equal to x is an identity function. Here, the for logistic regression, the link function was the sigmoid function. Okay, so the moment you keep changing these functions, you get potentially different models. Okay, and some models, of course, you don't want to pick arbitrary functions. There are some example functions that we'll see later as well. So that's what encompasses this class of generalized linear models. Okay, this kind of generalized on the model side, in addition to feature engineering that we mentioned at the beginning. So you can always create derived features, from the raw features that kind of further make the linear model quite flexible, right? So you can make it nonlinear by saying, hey, instead of just x as an input, I'm going to take x and x squared as an input. Now it's still a linear model, linear in terms of this derived parameters x and x squared, but not linear in terms of the original parameters, right? So what we're going to do before getting into GLMs is really a self-contained topic related to what is called an exponential family distribution. Okay, and the notion of what is called summary statistic. There's a nice idea to know if you've already not seen it in IDS 570, for example. And so we'll do that review first and then come back to generalized linear models, because the summary statistic idea is what's going to give us summary statistic as well as the definition of what is called exponential distribution. Sorry, not exponential distribution, but exponential family of distributions. It kind of ties the story of GLMs together. So there's some two concepts in between that we'll have to look at. So let's do that review. Okay. So, and that actually comes back to the word statistic. Okay. So statistic and statistics, I guess it's the plural. So we're going to first kind of review or just recap what a statistic means. Okay. Suppose we have a bunch of observations of a random variable. Okay. So we have a random variable capital Y, and its observations are y superscript 1 to y superscript m. Okay, so m is, think of the same m, 100. Okay, so we are seeing 100 different values of this random variable capital Y. Okay, so that is a shorthand. This is a shorthand. You don't have to write this way in your discourse, but this is just a shorthand to say this tilde just means, hey, drawn from this distribution. Okay, and the distribution, the random variable is y. This semicolon just shows that the second thing following the semicolon is a parameter. It's not a random variable. Okay. Suppose we have these m observations, little m observations, and actually let me quickly check if I have unmuted myself. Yep. And I don't know if I'm recording. Yep. Okay. So these realizations are, we don't know anything about the theta, which is parameterizes the distribution from which we got these samples. Whatever information we have is just the samples. Okay. And much of statistics as a field is all about going from samples to some idea about the parameters backing this distribution, these distributions. Okay. So there's a slight difference between probability and statistics. Okay. In probability, when you kind of define a probabilistic model, you don't worry about the data. You're just saying what is the data generating process, what is the conditional distribution, what's the joint distribution, and so on. Okay. So that's probability part. Statistics is saying, you got all these observations from some underlying model, like underlying probability distribution. It's all about the effort of trying to estimate the parameters, for example, of this distribution. So that's statistics as a field. But what is a statistic itself? A statistic is actually any function of these realizations. Okay. So and statistics is just the collection of these functions and their study, right? So this function t is a function of these m realizations of the random variable capital Y. So here are some examples. The mean statistic is just take these realizations, take an average, and second max statistic is just take the maximum. Median is take the median. So these are all statistics. These are just functions of these. So if you give me these 100 numbers, I can compute each of these statistics. Okay. So these are just functions of these realizations. There's also other functions. Okay. So for example, here's a function which takes the m realizations and produces a number 3. Okay, so something fixed. Okay, so it doesn't matter what the input is; it's just producing number 3. Okay, is this function a statistic? What does your gut tell you? Is this function a statistic or? So what are you guys not following? I guess let me ask that question. So is this function R a statistic? So it's a function of the data, right? But the function is such that it's always producing the number 3. Let's say, think of a Python function which like return 3. It doesn't matter what intermediate computation is happening, right? Do you think that's a statistic?
It's not changing. It's not a function. The function changes. The output changes.
It's a constant function. Like a function can always produce same number irrespective of what the input is. That's a constant function. This is a constant function. So given that I said it's any real value function of inputs, it is a statistic, but it's a useless statistic. It's not changing. Okay. So so of course, as I said, it's an arbitrary statistic, but it's not useful because it's a constant function. Okay. Ideally, you want a function of inputs which hopefully varies as the inputs vary, right? So I guess that's the difference from these other statistics that are given here, which is that compared to the last statistic, these other statistics, other functions, they summarize observations. So that's kind of the goal that we want. We want to define these. Ideally, we want to define these functions, or we want to work with these functions which kind of summarize observations, like the usual things that we've seen before, right? Even if we did not have the statistics vocabulary, we would say, hey, well, here's the average, here's the variation around the mean, things like that. We will use those words, right? So the statistic is just something that summarizes the observations. And so the question is, do statistics preserve the information in the samples? So there are a lot of words here which are kind of undefined, as far as how we like to deal with things. So do statistics preserve information? Right? So statistics by just mean, let's say, the mean statistic. Let's focus on the first one. So does the mean statistic preserve information? Okay, so it's unclear what the information is, but let's say samples, right? So we know what the samples are, y1 to y100, right? Does it preserve the information in the samples? Okay, so that is a little bit ambiguous, like what are we meaning by information? So clearly, if I tell you just the mean, you can't tell me what the individual numbers are, right? So that's we are certainly not preserving the individual realizations, but sometimes statistics do preserve something. Okay, what is that information? That's the information related to the underlying parameter of the distribution. Okay, so so the mean statistic can potentially inform something about the underlying parameter. Okay, so not always, but because there's so many statistics that we can create, arbitrary functions. But some statistics may be helpful in preserving some information about the distribution that generated this data. Okay, we're going to assume that there's some distribution. We don't know the parameter. From this, we got the data from which we computed the statistic. Hopefully, the statistic doesn't, of course, may not remember each and every realization, but may help us kind of preserve something about the distribution. Okay. So let's come back to this notion of statistics. Statistics is a function of the data. And there's also another word that we have used, actually, maximum likelihood estimation. Estimation had a word estimator, right? So estimator is also something that we estimate, is also something that we get from the data, right? So if you do maximum likelihood estimation, we are estimating something, right? We're estimating, for example, in the previous two MLE problems, we estimated the parameters theta. Okay, in the previous two, think of the linear regression case and logistic regression case, right? It's also based on data, right? So the question is, are estimators statistics? What do you guys think? So we've been using the word estimator informally, so far, I mean, we're not going to do any formal treatment of statistics, by the way, in this course. So because we said statistic is a function of data, estimator is also obtained from data. So it seems plausible that estimator is also a statistic, right? It is. And so we just use a slightly different vocabulary when we talk about estimation, which is like estimation of parameters. Okay? So so let's actually kind of verbalize this. So given independent and identically distributed samples, okay, so it's all these samples are coming from this distribution. It's unknown because its parameter theta is unknown, and all these realizations, samples, okay, they are independent. Okay, so y1 doesn't depend on what is the value of y2, or y3 doesn't depend on what is the value of y4 or y2, and so on. So a given realization has nothing to do with whether other realizations were high or low or whatever they were. Okay, so that's independent. Identically distributed because they're all being sampled from the same underlying distribution, same distribution whose parameter we just don't know. Okay, so each of these samples relies on these parameter or more than one parameters. Okay, and the estimation problem is basically of inferring theta given these observations y1 to ym. Okay, so that's the estimation parameter estimation problem. And one tool that we already saw briefly is the maximum likelihood estimation approach to estimate parameters, basically. So in the Bernoulli case, probability of y given theta is Bernoulli of theta. So I mean, we should just say Bernoulli. So y is Bernoulli random variable with parameter theta. Then probability of y given theta can be written this way. This was the exact short form that we saw even for the logistic case when we're talking about logistic case. So this is just a short form. We're just saying, hey, if y is equal to 1, it's theta. When y is equal to 0, it's 1 minus theta. Okay. Now let's say we observe y1 to ym, these 100 observations. Okay. Maybe we're flipping a coin. Heads means 1, tails means 0. And we are doing this maximum likelihood estimation approach. So we can compute theta hat, okay, which is the maximizing the likelihood. Remember, likelihood was likelihood, if each observation has a probability like this is, so the likelihood of the data is with such probability for each one of our m observations. Then this theta, then the likelihood function just becomes theta to the power number of heads times 1 minus theta to the power m minus number of heads. So what is this number of heads, right? So the sum over I is equal to 1 to m of yi. Okay, so yi, remember, is either taking value 1 or 0. So number of times it take a value 1 is exactly the number of heads. Okay, and number of times it took a value 0 is exactly m minus number of heads, which is the number of tails. Okay, so this is just I want to convince you that this is the likelihood function. Okay, and it's actually related to assignment question number 3 in question number 3 in assignment 2. Okay. So you have this likelihood function. You can maximize and get an estimator theta hat. Okay, your parameter estimator theta hat. And the summation of I is equal to 1 to m of yi doesn't preserve all individual information in the data set. For example, if I just tell you the summation, you can't tell me whether the first observation is 1 or 0 or last observation 1 or 0. So that information is definitely not there. But the summation of I is equal to 1 to m of yi has enough information for me to estimate theta hat. Okay, because remember, theta hat, if I want to estimate, I want to argmax over likelihood. And likelihood, I just need the summation of yi. I don't need the individual observations. Okay. So what we're trying to aim towards is this following property, that the summation of yi is sufficient to infer the parameter theta hat. Okay, and it turns out that the parameter theta hat is just summation of yi divided by m. If you actually do the maximum likelihood, maximize the likelihood here, it turns out that the theta hat has actually a formula. Instead of just doing gradient descent here, it has a formula which is just the average. Okay, it's just sum over number of times heads happen divided by number of times you actually flip the coin. Okay, that's the estimator for what is the bias of your Bernoulli random variable. Okay, so just the summation is sufficient. Okay, and just to contrast the other statistic, we saw in the previous slide, this statistic is of course not at all useful in providing any information about theta. But this statistic, this sum statistic, is sufficient to infer the parameter theta. Sufficient in the sense that you don't need anything else; you just need that. Okay. So the word sufficient was bold-faced because was colored red because we're going to talk about it in next slide as well. But just to give you more, stepping back again, statistics is all about compression of information in observations. Okay, so you collected data. You assume that there's some underlying distribution from which you got the data, and you're gonna, statistics are just these compressed functions like the T function that we saw, summations, averages, max, mean, median, and all that. And then some statistics are useful to actually reverse engineer what could be the, to suggest what could have been the parameter that gave rise to this data. Okay, through, for example, the maximum likelihood estimation approach. Okay, not all statistics are useful. So if I create all sorts of functions, some functions I may not be able to tell you what the theta is, but some functions can. And we saw in the last slide, summation of yi was able to tell us what the theta is. Okay? Summation of yi divided by m was actually the estimate of theta, right? So the key idea, and that's why sufficient was bold-faced, I guess in the previous slide, is that the sufficient statistics are enough. Just have enough summary of the data. So you had the original data with all the observations. You kind of string them and say, hey, here's a summary, the average or sum, and that is enough to kind of point us towards an estimate of theta. Okay, they're enough to infer or estimate theta. Infer, estimate is the same thing for now. Okay, so this is a problem, right? So this is the original problem. Given data, each sample relies on an underlying unknown parameter theta, and parameter estimation is estimate or infer theta given the parameters to the best of our knowledge. So given the samples to the best of our knowledge, and a statistic is said to be sufficient, okay, for theta if the conditional distribution of these y1 to ym realizations, okay, given the sufficient statistic and theta does not depend on theta. Okay? So this is just a technical condition for when can a statistic be sufficient. So instead of like thinking of this conditional distribution expression, what we want to say is that given t, we cannot get more knowledge about theta, okay, by we cannot gain more knowledge about theta from knowing more about the distribution of these random variables. So t kind of is enough to get theta, and it's not like if you know the original data set, you will be able to estimate theta better. Okay, that's why this is a sufficient statistic. Okay, let's go with that working definition. Yeah.
Is that a hypothesis or is that
So we're defining, so statistics are any functions of data, any functions of observations, realizations. We are defining which one of these statistics can be called sufficient. Okay, sufficient is like an adjective that we want to say, hey, these are statistics which are sufficient, these are statistics which are just arbitrary statistics. Okay, so which statistics can be sufficient? Those statistics these are statistics which are such that you cannot gain more information. You cannot get more information about the underlying parameter by once you have the statistic. Looking at the original data or creating other functions, it does not help you more for estimating the underlying parameter.
only those that are
If a particular statistic is sufficient, if adding more information kind of doesn't change your it doesn't change anything in the sense that the sufficient statistic is enough to estimate the theta. Okay. Anything else is not useful. Anything else in the sense that, remember, what would be the most base case sufficient statistic? So if you have the original data, you can just call that as a sufficient statistic, right? Because that that is also some function of the original data. It's yeah. Because t is a random variable. So a function of a random variable is a random variable. Is your question about this expression here? Yeah.
The values of t are not making any changes to the statistic like the probability.
No. So there's a joint distribution over the examples, right? And so t is a function of those examples, right? T is also a random variable. We're just saying that given t, actually there should be a semicolon here, but given t and theta, this conditional probability does not depend on theta. Is the claim? Yeah, this random variable capital T taking a value small t. Yes.
So that's why I'm using any value for small t. Like if that is not dependent for anything, then why am I using small t?
You're saying so okay, there are a couple of steps going on here. First of all, capital Y i's are also random variables, right? That's clear. So your question is, so t is a function of these realizations. So these are the same random variables. T is also a function of those random variables, basically. Now I'll tell you what the realization of the t is. Okay, so summary statistic is 100 units. Okay. That does tell us something about the distribution of these guys, because these cannot be arbitrary numbers, right, anymore. These random variables have to be such that they sum up to, for example, 100 units. Not sum up to, I mean, it depends on statistic, but if you're using some statistic, so it does telling you about t does change the distribution of the conditional distribution of these guys. Okay, so it's not that t is independent of these, but I don't want to confuse the rest of the class. Okay, so folks who are losing attention, the point is we're just saying statistic is just a function of data, any function of the data. Okay, or if you just call the original data, that can also be a statistic. Typically we care about what I call minimal sufficient statistics, but let's say a statistic is any function of data, and we want to say that some of these statistics are sufficient statistics if if you have the sufficient statistic, some function of the data, then the original data or any other data is not useful for estimating theta. Okay, just the sufficient statistic is enough. It's sufficient since it's in the name. Just that function of the data is enough. The original data is also not useful anymore. Any other, if you give it a sufficient statistic and say, hey, first sample was this, second sample was this, can you tell me better estimate of theta? It's not useful. You cannot use that. Okay.
Any name of few?
Yeah, we'll see. In fact, all the usual things that you saw, like average is a sufficient statistic for, it depends on distribution. Okay, so so sufficient statistic is not something completely unrelated to the distributions that we care about. So depending on what this distribution is, you'll have a sufficient statistic. Okay, so basically the idea is compression. Okay, so statistic by definition is it's like compressing data. Okay, it's like function of the data. So generally you take an average, the usual things that we naturally do, average or standard deviation, estimated standard deviation, so on. So basically we can only keep t and throw away all the data without losing information. Again, information here informally just means information related to the underlying distribution. Of course, we lose information which is the sample realizations themselves, but we don't care about that. We care about the underlying distributions parameters actually. Okay, so for example, this summation is a sufficient statistic for the M Bernoulli trials. Okay, we don't need to know exact whether the first one was heads, second one was tails. We don't need to know that. Just how many heads happened out of, let's say, 100 trials is enough to kind of get an estimate for the parameter of the Bernoulli. Okay. It's not a complicated concept. I mean, so not just the summation. So it can be also the average. Okay. So all I'm saying is, if you know the summation is a sufficient statistic, you can just multiply and divide it by constants, and it will also be a sufficient statistic. Okay. So why do I want to talk about sufficient statistic is because it helps us define this exponential family of functions, distribution, sorry, exponential family distributions, okay, of which normal distribution and Bernoulli distribution corresponding to linear regression and the logistic regression are members. Okay, and so not just linear regression, logistic regression. There are many other types of regression that you can do, and that's exactly the idea of generalized linear regression. Sorry, generalized linear models. So in Bernoulli trials, the dimension of the sufficient statistic is 1, which is the dimensionality of the parameter itself, the bias, the flip, what is the bias of the coin itself. Okay. So if we have a lot of samples, but in general, if we have a lot of samples, let's say m, okay, if we 100 observations instead of 100 observations or 1000 observations, then in some cases, situations, we may not, the summary statistic, just one summary value, like let's say t is equal to one number in the Bernoulli case, right? The average, the sum may not be enough. Okay. Actually, the right point I want to make is that for some underlying distributions, you may need many summary statistics to be able to estimate the parameter theta. Okay. So for some distributions, okay? Some distributions may need lots of summary statistics to estimate the underlying parameter theta. Okay. So when you have more and more data, you can estimate many statistics, and maybe all of them are useful to estimate underlying parameters. But there is a good family of distributions, okay, this P of y given theta, for which the number of sufficient statistics that you need. Okay, so each statistic, let's say it's a function which produces a real number, right? Average is a real number, max is a real number, and so on. There's a good family of functions for which the number of sufficient statistics that you need is the same as the number of parameters that you're estimating. Okay. So for Bernoulli, there was only one parameter, so we didn't care. But for example, think of normal distribution. There could be typically two parameters, right? The mean and the variance. So some distributions could have more parameters. Okay, so there are some distributions for which the number of sufficient statistics is the same as the number of parameters, no matter how many samples you have. Okay, so even if I have 100 samples or whether I have 1000 samples, the number of sufficient statistics I need to compute is the same. Okay, so that good family is called the exponential family. Okay, it's called the exponential family of distributions, and it's kind of the workhorse, or it's kind of is what leads to generalized linear models. Okay. So let's actually spend a couple of minutes on what is an exponential family, and then relate it back to the two special cases that we saw, linear regression and logistic regression. But not just, if those are the only two things, then that would not, there's no point studying generalized linear models. The point is, there's a general template that you can use for other situations. For example, your output variable need not be just numeric. I mean, it can be numeric and categorical as in a classification regression. But what if you also know that the output variable is only takes integer values? Okay. What if your output variable is actually counts? Okay, so you know that it only takes positive values. Okay. So now you can say, hey, if it's only taking positive values and only integer values, although it's numeric, should I still think of it as a normal distribution? Probably may or may not be a suitable idea, right? So that's where you can kind of use the idea of generalized linear models to come up with your own model. Okay. And so let's talk about this probability of random variable taking a specific value little y given what is called a natural parameter eta. Okay, so eta is again a Greek symbol. It's just think of it as a parameter. Okay, so we're gonna say, so exponential family is actually a distribution, is a family of distributions. Okay, of which normal distribution is a member, Bernoulli is a member, and they all have this type of an expression, which is this probability of y given eta has basically three terms. Okay, so there's a multiplication term which only depends on y, doesn't depend on eta. Okay, only depends on phi, which is it's a function of y only. Then there is an e to the power. Then there's the first term which only depends on eta. Sorry, which depends on eta, and it depends on eta and a function like t of y. Okay, inner product between them. And then there is a third component which is a of eta. Okay, so it only depends on eta, doesn't depend on y. Okay, so this part doesn't depend on y. This doesn't depend on eta, and there's a part which involves eta and some function of y in a particular way, which is like an inner product. Okay, but it's in the exponent. Okay, so I want to just spell out some names here. So eta is called natural parameter. Why the name natural? Because it may not be exactly the same parameter as the way we define. For example, when we define Bernoulli distribution, we say what is the bias of the coin? Bias of the coin is 50%. Then Bernoulli distribution has the parameter 0.5. Okay, that 0.5 is not exactly the same as the natural parameter. Okay, so if you want to define Bernoulli distribution in the language of exponential models, say that's an example of exponential models, then the eta will be slightly different. Okay, it's different than 0.5 that will report. Okay, but they are related, of course. So eta is called natural parameter. It's related to what are called user parameters. Generally, the usual things that we see: mean, variance, bias of Bernoulli, and so on. Those are called user parameters. This eta is related to that user parameters as well as if there is extra input. Remember, for both linear regression and logistic regression, there's a given x. There's a input feature which we don't talk about its distribution and all that. We only think of there's an already given input, so we don't care about its properties, its distribution and so on. Okay, so eta is a natural parameter. A of eta, it's called the log partition function. It basically is just there to ensure that this is a distribution, which is that if it's a distribution, if it's a continuous distribution, if you integrate over the values the random variable is taking, it should be equal to 1. If it's discrete, then if you sum over all the values the random variable can take, it should be 1. Right? This A of eta is just ensuring that will ensure that this summation is equal to summation or integration of this left hand side is equal to 1. Okay? It's called log partition function. So let's ignore that. That's not super important for our discussion. The next function is called b of y. It's called the base measure, or it's just a function of y, which is called the base measure. Okay, so I don't want to get into the detail of that. It's just a function of y. Okay, so it doesn't depend on eta. Okay. And t of y is called the sufficient statistic. Is the natural sufficient statistic. Okay, so you can see that the definition of the probability distribution itself is defined in terms of the sufficient statistic. Okay, so it's a function of data that yields sufficient statistic in aggregate. So T of y is a natural sufficient statistic. Natural just because eta is a natural parameter, and there's some extra two functions, A of eta and B of y, which are just there to ensure that this is actually a distribution. Okay, kind of is a well-defined distribution. So what I introduced in this slide is just the moving parts of this expression here, and this expression here is what any member in this family just means a collection. Okay, any member in this collection of distributions which you're calling as the exponential family conform to. Okay, as a teaser, I'm just saying that the normal distribution and the Bernoulli distribution will have expressions like this. Now you may say, hey, normal distribution has some square term. Where is the square here? You cannot like pattern match, right? But that square is not an issue. In fact, normal distribution will also be like this. Okay, so we'll see that later. Okay, so let's look at Bernoulli distribution. P of y, Bernoulli exactly the parameter. So P of y given the parameter phi is equal to phi, right? The parameter is phi. And we know that we can write in short form like this. If parameter is phi, then phi to the power y, 1 minus phi to the power 1 minus y, right? Now what we're going to do is massage this into that exponential distribution definition. Okay, so how do we massage it? It's e to the power log of this. Okay, so e to the power and log just cancel out, so we just add an extra log and extra e to the power. Okay, so what we're doing is just massaging it into the expression that we in the previous slide. Okay, so we just add an e to the power and log, okay, of the same thing which was there before, and then log of the terms inside. If we just collect it together, the inside becomes like this. Okay, log of phi by 1 minus phi times y plus log of 1 minus phi. Okay, so it's just a log of a to the power b plus a to the power b times c to the power d type of a situation. Now you can actually, just by looking at this expression, you can now talk about what are the corresponding exponential families parameters. Okay, so let's start with b of y. There is no coefficient in front of exponent, so let's let's think of b of y as 1 base measure. Now if you look at the exponent, there are two terms. There's one term which is a function of phi, and there's one term which is a function of y. So t of y is just y, because there's only one term which is a function of y, it's just y itself. Okay, and the thing which is multiplying y, we're going to call it eta. Okay, so log of phi by 1 minus phi, we're just calling it eta. Okay, and whatever is not a function of y at all, we're just going to put it as part of a. Okay, a of eta is just minus of log of this. Minus because if you remember the template, there was a minus. Okay, so minus of minus is just plus, right? So that's the log partition function. Okay, so this was the mapping. So just trying to show that Bernoulli random variable, Bernoulli distribution is a part of the exponential family. Now similarly, is this the last slide? Let me go to this. I should not have scrolled so much. Yeah. Okay, so we saw the example of how Bernoulli is a member of this family, and what we want to spend now time is to kind of say, hey, how do we estimate the parameter of this family? Okay, so what is the parameter of this family? Eta. Okay, which is called the natural parameter. It may be slightly different from the parameter that you typically define when you define Bernoulli of Bernoulli with bias or something, right? So remember, for Bernoulli, eta was equal to log of phi by 1 minus phi. Okay, so that was eta. So if you have a data, right? So probability of y1 to, if you have data, you can write the likelihood as a function of eta this way, right? So it's by just inserting the definition of the exponential distribution, right? The typical exponential distribution. Probability of data would be product over m observations of the probability of each of the observation, and you can take the product of the first few terms as is, and the product for the next bunch of exponent terms, you can take the product into the exponent, which becomes a sum. Okay, so sum over t of yi minus however number terms there are, there will be an m there, which is just the number of times an has to be added. Okay, now you can see that from this product of bi. Okay, so let's focus on this. So product of b of yi is not affecting the estimation of theta. So in the sense that, think of this as a likelihood, right? This is a likelihood. We just wrote the likelihood explicitly as a function of the definition of the exponential family. This is the full expression. You can see that this doesn't have anything to do with theta, whether eta changes from eta1 to eta2. This term is not a function of eta, so you can ignore it, okay, because we care about estimation of eta. Okay. Now, if you look at the second term, eta does appear in both here and here. Okay, but the term which is the only term which is data dependent is just the summation term, summation of t of yi. Okay, this is the only term which is affecting the eta estimation. Right? So if I slightly change the data, then the summation changes, and if the summation changes, eta may change. Right? So the summation of t of yi is the sufficient statistic for any distribution in the exponential family. So we spent like 10 minutes on trying to go to the exponential family. The punchline is that you have the original data, so y1 to y100, y1 to y1000, whatever it is. From there, if you can get to this summation of t of yi, that is enough to figure out what eta is. Okay, that is enough to figure out what eta is. Okay, because that's the only, if you look at the log likelihood function, this is the only thing that is function of data. There's nowhere else data is appearing. So as long as you can, from original data, as long as you can compute this aggregate, the aggregate will lead you to the right eta. Okay, of course, you still may have to do some optimization. You may still have to find out what is the eta for which the likelihood is the maximum and all that. But so this is a sufficient statistic. Okay? So that's why we introduce the word sufficient, what is the statistic, and so on. Okay. So now let's come back to a different example. Previously we saw Bernoulli. Now we're going to talk about binomial. Okay. How are Bernoulli and binomial related? So Bernoulli random variable is x. Let's say let's say there are 10 Bernoulli trials. 10 times I flip a coin. Then each Bernoulli, so each time I flip a coin is a Bernoulli random variable. Can land heads, can land tails. Okay. Then a binomial random variable is a sum of these 10 Bernoulli random variables. Okay. So binomial random variable is just a sum of these Bernoulli random variables. Okay. So typically, so let's say there are n binary trials or Bernoulli trials. Then the distribution function is like something like this. Okay, so it's m choose y. Okay, so you are saying in n trials, how many times, let's say y is equal to 3. How many times would you get 3 heads? Okay, that is 10 choose 3 times the probability you can get a head to the power 3, and 1 minus probability you can get a head to the power m minus 3. Okay, so this is just the definition of the Bernoulli distribution, by the way. Okay. Now again, what we want to show in this slide is that this is also an example of an exponential distribution. Okay, so if you kind of look at this expression, right? So you can create, there's a to the power y and a to the power minus, to the power m and minus y. So you can actually 1 minus p to the power m, you can separate it out, and then you can have a term which only depends on y, and then again use the x log relation. So you just apply a log and then an exponential operation. So log of this term, the second and third term, log of the second and third term, the second term leads to m log of 1 minus p. That's like your minus a of eta. Okay, and the third term leads to y log of p minus 1 minus p. Okay, so that's like your eta times t of y. Okay, t of y again is y. Eta is log of phi by 1 minus p, and your you can say the base measure is m choose 1. Okay, so we're just trying to say, hey, if this is the expression, can we just map it back to our general template of the definition of an exponential distribution? Okay, so again, you can see that the natural parameter for binomial distribution is the same as the natural parameter for the Bernoulli distribution. And it's related to the what is called the user-friendly definition of Bernoulli or binomial distribution, which is phi. Okay, phi is the probability of success. Right? So Bernoulli and binomial have the same natural parameter. Okay. So now let's look at the more interesting example. So we have this exponential distribution. We saw Bernoulli. We saw binomial. Let's look at Gaussian. Okay, just trying to say that all these are exponential, right? So we know that the distribution of Gaussian random variable, one-dimensional Gaussian random variable, is something like this. Okay, with a multiplier, exponent, and a square term. Now you may say, hey, now we have a square term. How do we deal with the template for exponential distribution? Did not have a square term, but we in fact just expand the square term. You have y, a term involving y, a term involving y square, and term involving nothing to do with y. Okay, so y, remember, is our generic realization of random variable. Right? So what you can do is group things together. So just 1 by square root 2 pi, keep it separate. This sigma you can convert into log of sigma, because sigma here is e to the power log of sigma, same thing. Okay, this sigma here. So what you have is, because of this expansion, there are so there are two terms which involve y. So mu by sigma square and 1 by 2 sigma square. Just think of that as a vector, for here row vector, and then y and y square as like a column vector. Okay, so you have a row vector times a column vector, some sort of inner product, and then you have a term which doesn't involve y. So just we are collecting them so that we can just call them together to define the log partition function. Okay, the extra a and a eta terms that we have. So if you just now pattern match again, now your natural parameter is natural parameter is mu max sigma square and minus 1/2 sigma square. Okay? Whereas the user-friendly parameters were just mu and sigma square. So when you define normal distribution, you just say mu and sigma square, mean and variance. Right? Here the natural parameter is something slightly different. The sufficient statistic. Okay, let me not look at this, but see. Yeah, here the next two lines are just deriving so deriving mu and sigma in terms of these parameters, eta 1 and eta 2. So let's ignore these two lines for now. Okay, it's just trying to show that, hey, if you have the natural parameter, there are two dimensions, two numbers, then how are they related to the user-friendly parameters mu and sigma square? Okay, so the log partition function is just the remaining part here. So mu, it's mu square by 2 sigma square plus log sigma. Okay, this term here, and the important thing is the sufficient statistic. Okay? Sufficient statistic is y and y square. Okay. Now this is an example where the sufficient statistic dimension is not the same as is not one dimensional. Okay, the Bernoulli and binomial case, it was just one dimensional. It was just some sort of an average. Okay, so here the sufficient statistic is both the observation and the square of the observation. Okay? And if you think of log likelihood, there's a summation involved. And the base measure is some constant function. Okay, so this kind of shows that again a normal distribution with one dimension, or a normal distribution essentially is also a member of the exponential family. Okay, so since Gaussian distribution is parameterized, I mean, to just summarize, the Gaussian distribution is parameterized by two numbers, generally mean and a variance. That's why you see that the sufficient statistic also has two dimensions. Okay, so y and y square. Okay. And so what is the right statistic? So if you think of the aggregate, if you have m observations, then the statistic sum of I is equal to 1 to m of yi and sum of I is equal to 1 to m yi square are enough to kind of estimate the mean and variance. Okay, of course, to get to mean and variance, first you kind of estimate the natural parameters eta 1, eta 2, and then from eta 1, eta 2 you can estimate mean and variance. Okay, so you don't need to keep the full data. Basically, that's the idea. Okay, so let's come back to our original motivation. Why are we studying sufficient statistics? We are studying them because we want to go beyond logistic regression and linear regression. We still want to use the strength of linear models, but we want to go beyond those two. And what we did is look at those two, the distributions kind of motivating those two, logistic regression and linear regression, happen to be Bernoulli and Gaussian. They are just members of exponential family. And so we can, and since they are members of exponential family, there are other members of exponential family as well. Okay, there are many other well-known distributions. They have some nice properties, these exponential families. The dimension of the sufficient statistic doesn't change. Okay, it's exactly the same as the dimension of the parameters that are involved. Okay, and distributions just you can get different members of this exponential family by just changing the base measure, just changing the sufficient or just changing the sufficient statistic or changing the a. So basically these are plug and play, right? So b is a plug and play, t is a all the functions involved here, three functions are plug and play. So let me skip those 2 points there. But we're studying exponential families because they are basic ingredient for defining generalized linear models. Okay, so in the next slide, let's quickly define them. For example, a new regression which you've not seen is Poisson regression. Poisson random variable. It's a count random variable. Okay, so it captures counts, right? So here is a example. Okay, so how do we use this exponential family? So let's say you have been given a regression or a classification problem, which means that we want to predict y as a function of x. We want to do we were going to make 3 assumptions. Okay? So 3 assumptions. So this example is already showing in the logistic regression case, we made the assumption that y given x is Bernoulli. Okay, where the phi function, so where the Bernoulli bias is g of theta transpose x. Okay, so what we're going to do is that we're going to generalize that as saying, hey, y given x is an exponential family distribution, is exponentially family distributed with parameter eta. Okay, of course, there's a relationship between theta and eta, so let's ignore. So what we're saying is that where eta is just a function of theta and x. Okay, and that you can see here, phi is a function of theta and x here. Okay, Bernoulli bias. So that's the assumption. So we are saying, as long as you can say that y is a function of x, is exponentially distributed with eta being a function of theta and x, that's one assumption. Second assumption is that we want h theta of x to be the expectation of the sufficient statistic given x and theta. Okay, so remember, sufficient statistic is a function of these random variables. It's also a random variable. So we just say that h theta of x is exactly defined this way. Okay, so which is the expectation of this sufficient statistic. Okay, which means that h theta is just the expectation of if t of y is y, then h theta of x is just the expectation of y given x. Okay, so in the linear regression case, this was true. Expectation of y given x was exactly h theta of x. Okay. For the Bernoulli case, expectation of y given x is actually g of theta transpose x, where g is a sigmoid function. And the last assumption is that eta, how is it eta related to theta and x? It's just linearly related. Okay, eta is actually equal to theta transpose x. So we make these 3 assumptions, that y given x is exponential family, eta is equal to theta transpose x, and h theta is actually just the expectation of the sufficient statistic given x and theta. So under these 2 assumptions, we get a general recipe for any output variable. So think of output variable which is continuous, but maybe is integer and is maybe positive valued. Then you can choose an appropriate distribution belonging to the exponential family. Okay, and the h theta, you want to say that h theta of x is just the expectation of this sufficient statistic corresponding to the exponential family, and that eta is equal to theta transpose x. Okay, natural parameter and the inputs are related linearly through theta. Okay, so this is the linear part. Okay, these 2 are the generalization beyond these 2 are the generalization which kind of may let you go beyond linear regression. Okay. So for example, h theta for logistic regression happens to be the sigmoid function in addition to the linear function, and this exponential family happens to be Bernoulli. Okay. So I think let's actually come back, and I'll briefly recap this if it was too dense the last few minutes, and then we'll go over to some examples like multi-class logistic regression. So far we've been talking about binary case. I'll make some connections to the multi-class situation, and then we'll move on to the next topic. Okay. So if you have any questions about this, you can come to me and we can discuss. Okay. So far what have we seen? But just recap, we looked at logistic regression. We started with logistic regression, and then we were trying to generalize to what is the statistic, what is the sufficient statistic, so that we can define the exponential family. Then we showed some members of the exponential family, like the Bernoulli, the binomial, and the normal distribution. And then we were trying to get towards a template for what if my output variable is count data or some other data. Then there is a template for how to extend beyond linear regression and logistic regression. So we'll come back to this and then move forward. Okay, next time.